In this video, I want to do some examples of sample distribution problems and then talk about the central limit theorem. 80% of students at a large university are receiving scholarships from the school. What is the probability that a sample of 200 students will find less than 145? Okay, so this is a sample proportion problem, right? This is our P, 80%, and our sample proportion, our P hat, is 145 divided by 200, which is 0.725. Okay, so that's our P hat. So for proportion problems, our two conditions, we should start with our conditions. Of course, we want a simple random sample. That's kind of that zero condition. Our first condition is the sample size should be less than or equal to 1/10 the population size. This says it's a large university, so I think we can be pretty safe in saying there are more than 2,000 students. Okay. Our second condition for proportions is that the sample size multiplied by the probability, the P, which in this case is 160, has to be bigger than 10, and 200 times the complement, which in our case is 40, must be bigger than 10. So we have met both conditions to proceed through this problem. So we do this, we do a normal curve. This is normally distributed with a center at 0.8 and a standard deviation of 0.8, 1 minus 0.8 over the sample size. And we are looking at the probability, if we're centered at 0.8, 0.725 would be here. So we shade that. So there is our final probability, 0.004. So pretty improbable to find that low a proportion. A hotel chain claims that the average stay for its business clients is 5 days with a standard deviation of 2.3. Find the probability that a sample of 50 of these clients yields a sample mean of 6.1 days or more. So once again, that kind of, we hope it's a simple random sample. Our condition for this, we only really have the one now, and that is that 50, our sample size, should be less than or equal to 1/10 the population of all clients. And this is a hotel chain, it says, so we're going to assume that, yes, there are more than 500 clients. So we can proceed. So we have a normal curve. This is going to be centered at 5. Now you'll remember, the difference between the old problems and the new problems, the old kind of normal curve problem would have said, what's the probability a client stays more than 6.1? And that would not be that unreasonable to expect. But this is saying we took a sample of 50 and the average was 6.1. So we modify our deviation because a sample mean should have less deviation from 5. So it's 2.3 over the square root of n, or for us 50. And we want to know 6.1 or more. And here is our answer. And you could make sure that the work that you can do that. I want to just point out one thing. This sign, this notation, of course, means you move a decimal 4 places, so it's actually 0.00036. There's 3 zeros in front. Please be careful. Every once in a while, someone will type this in, and then they'll just say, "Oh, the probability is 3.6." Well, probability needs to be between 0 and 1. So use your number sense here about probability too, and don't forget to read the entire line. The strength of paper coming from a manufacturing plant is known to be 25 pounds per square inch with a standard deviation of 2.3. In a simple random sample of 40 pieces of paper. Okay, so again, let's just check that condition. 40 pieces of paper. Boy, this is a manufacturing plant. They better be making more than 400 pieces of paper a day. So we'll do that. Okay, so we fulfill. So we got a normal curve. The mean was 25. Standard deviation we took is going to be 2.3 over the square root of 40. And we're wondering about being between 24.5 and 25.5. With that. So you can see a pretty healthy proportion of the curve, or the probability is very high that it will lie in that range. All right, so we had already talked about estimators, but I just wanted to make sure that we talked about the fact that we use a sample to estimate a population, and therefore we use a statistic to estimate a parameter. So the notation here is that X bar, the statistic, estimates mu, the parameter. And for proportions, P hat, the statistic, estimates P, the proportion. And finally, I want to talk about central limit theorem. Central limit theorem is a very big idea, and actually in the last video I showed you some animations of sampling distributions and how if the distribution was normal to start with, the distribution of the sample means was normal very quickly with any sample size. But if the distribution was non-normal, then it took a larger sample size to get the distribution to appear normal. So this is central limit theorem. And again, you could go back and watch those animations again if you wanted. If you have a simple random sample of size n, if the original population, we sometimes call this the parent population, was normally distributed, then so is the distribution of sample means. Okay? It's simple enough. If I tell you the original distribution of heights is normally distributed, then you can assume that the sample means of heights are normal, regardless of sample size. However, if the original parent population was not normal, like that one I showed you, a uniform distribution, then we need a larger sample size. 30 is kind of industry standard in order to assume that the sample means will be normal. And again, go back and watch that animation if you'd like to. That showed that progression, that it takes a larger sample size in order for the sample means to appear normal. So this becomes the second condition for sample means. Okay? So that first condition is that 1/10. This is the second. So in both of the problems we've done in this video, we had 50 clients at the hotel. Perfect. That's over 30. Doesn't matter what the distribution of staying at a hotel is. We had over 30. In the second, we had 40 pieces of paper. Perfect. It's over 30. We're done. If you have a sample size less than 30, you need some information. You need to know about the parent population. Was the parent population normal? Or we need to do some checks of our sample, and we'll talk about that more as we go on. But keep this in mind. That is our second condition for sample means. As I said, we achieved it in both of the problems we did today, but keep an eye out for that magic number of 30.